Throw a ball straight up and it comes back down. Throw it harder and it climbs higher before it falls. Throw it hard enough, faster than about 11 kilometers per second, and it never comes back at all. It escapes Earth entirely. That speed has a name: escape velocity. Now here's the question that opens a door in the universe. What if gravity were so strong that the escape velocity was faster than light itself? Then nothing, not even light, could ever get out. That is a black hole. Escape velocity depends on two things: how much mass is pulling on you and how close you are to it. More mass or less distance means a faster escape. So you can make gravity fiercer in two ways: pile on more mass, or take the same mass and squeeze it smaller so you can stand closer to its center. Keep squeezing and the escape velocity climbs and climbs. Squeeze enough and it reaches the speed of light, the cosmic speed limit that nothing can beat. At that moment, light itself can no longer leave. The object goes dark. It becomes a black hole, not because it's empty, but because its gravity has sealed it shut. The size of that sealed region has a precise formula, worked out from Einstein's relativity by Schwarzschild in 1916, within months of the theory itself. It's called the Schwarzschild radius, and it marks the point of no return. Cross it, and no signal, no light, no rocket, however powerful, can ever climb back out. That boundary is the event horizon. And here's the strange part: it isn't a wall or a surface. There's nothing there to touch. It's simply the line beyond which the future leads only inward. How small is it? Squeeze the entire sun down to a ball about 6 kilometers across, and it would become a black hole. Squeeze the whole Earth, and its horizon would be no bigger than a marble. Nothing squeezes them that hard in everyday life. It takes the collapse of a dying star, gravity crushing inward with no force left to hold it up. So what would happen if you fell in? Let's take the plunge carefully. Gravity pulls harder the closer you are. Fall feet first toward a small black hole, and your feet are tugged much harder than your head. The difference stretches you. Stretched lengthwise and squeezed at the sides, you'd be drawn into a thin strand. Physicists have a wonderfully grim name for it: spaghettification. But something even stranger happens to time. To someone watching from far away, your falling clock appears to tick slower and slower as you near the horizon. Your light stretches, reddens, and dims. From the outside, you seem to freeze at the edge, fading forever, never quite crossing. Yet from your own point of view, nothing special happens there. You sail across the horizon in an instant, and it's already behind you. Once across, all paths lead the same way. Inside the horizon, the center isn't a place you could steer around. It lies in your future, as unavoidable as tomorrow. In a sense, space and time trade places. Moving forward in time now means moving inward, toward the center, no matter which way you turn. And at that center, Einstein's equations scream. They predict a point of infinite density, where space and time curve without limit. We call it the singularity. But infinity is usually physics admitting defeat. The singularity is really a signpost. Here, general relativity breaks down, and we'd need a theory of quantum gravity, which we don't yet have, to say what truly lies inside. This all sounds like pure theory. So how do we know black holes are real and not just mathematics? Over the last decade, 3 different windows opened. First, the motion of stars. At the center of our galaxy, astronomers tracked stars whipping around something unseen. One star, Estwo, orbits an invisible object about 4 million times the mass of the Sun, packed into a region smaller than our solar system. Nothing but a black hole fits. That discovery earned a share of the Nobel Prize in Physics in 2020. Second, ripples in space itself. In 2015, the LIGO detectors felt a tremor from 2 black holes, around 30 solar masses each, spiraling together over 1 billion light-years away. Their collision shook the fabric of spacetime, and we heard it as a gravitational wave. Third, an actual picture. In 2019, the Event Horizon Telescope, a network of radio dishes spanning the whole planet, released the first image of a black hole, a giant in the galaxy MADI 7. In 2022, they imaged the one at the heart of our own galaxy. We don't see the black hole itself, of course. We see its shadow, a dark circle rimmed by the glow of hot gas swirling in before it falls past the edge. The darkness in the middle is the horizon. Black holes come in wildly different sizes. The smallest we've confirmed form when a massive star runs out of fuel. Without the outward push of fusion, gravity wins, and the core collapses in a heartbeat. Those stellar black holes weigh a few dozen suns, packed into a city-sized horizon. Ironically, near a small black hole the stretching is brutal, so a stellar one would spaghettify you long before you reached its horizon. At the other extreme sit the supermassive black holes, millions to billions of times the sun's mass, lurking at the centers of galaxies, including ours. How they grew so vast so early is still an open puzzle. Strangely, the bigger the black hole, the gentler the crossing. A supermassive giant is so large that the difference in pull across your body is mild, and you could drift past its horizon without feeling a thing, even as it seals your fate. For decades, black holes seemed truly eternal. They only swallow, never give back. Then in 1974, Stephen Hawking found a crack in that idea. Combining gravity with quantum mechanics, he showed that a black hole isn't perfectly black. Right at the edge, quantum effects let it leak the faintest whisper of radiation. Slowly, it loses mass. Slowly, it shrinks. But slowly barely covers it. A black hole, the mass of the sun, glows at around 60 billionths of a degree above absolute zero, and would take something like 10 to the 67th power years to evaporate, unimaginably longer than the current age of the universe. And that leak hides a deep mystery. What happens to everything that fell in, all its information, when the black hole finally fades to nothing? That single question, the information paradox, still splits physicists today. A black hole is what's left when gravity wins completely. A boundary in spacetime past which the universe keeps its secrets, sealed behind the one edge that light itself cannot cross. We can trace the stars that orbit them, feel the waves when they collide, and photograph their shadows against the glow. But what lies at the very center remains, for now, the deepest unanswered question in physics.